Hello everyone. Today we're going to continue on where we left off yesterday. So yesterday we learned the definition of linear function and also the set true that your 8th grade math teacher been lying to you and calling f of x equal to mx plus b a linear function. Well, it actually is not. But to be fair, y equal to mx plus b or f of x equal to mx plus b is considered to be a linear function in the idea that it is a polynomial. But in terms of linear algebra, it's actually not a linear function because of the plus b part that's kind of mess it up. So what are we going to talk about today? Well, today we're going to talk more about linear function, and the most important thing would be how to represent linear function. Because they have this very important property that allow us to actually evaluate a linear combination of this input as a linear combination of the output. Therefore, allow us to kind of reverse the process of, okay, form the linear combination first and then plug into the function. Or I can actually choose, remember option 1, option 2 from yesterday, to actually form the value of the function first and then form the linear combination. So it's a very powerful property that allows us to do things quite differently and give us this great flexibility in evaluating or doing problems involving linear function. So then how do we actually represent a linear function? Well, this is theorem 13.1.3. I'm sorry, 3.1.3. So basically just mean chapter 3, section 1, theorem number 3. 1 and 2 are not important, so we didn't talk about it. Which basically states the following. Let's say given a function f that maps from Rn to Rm. If the function f of vector x, and here vector x is in Rn because that's the domain of the function. Let's say if f of x is linear, is a linear function, then this must be true. Then the function f of vector x can be represented as a matrix function. In the form of f of vector x equal to some matrix A multiplied by vector x, where matrix A is an m by n matrix with columns formed by the vector f of vector e1, f of vector e2, to f of vector en. So you may not remember what those vectors are, and we'll talk about it in a little bit, but first thing I want to point out would be this. Right here, A is a very specific matrix with a very specific dimension that represent based on the function f. So notice the function f maps from Rn to Rm, and the matrix A is actually m by n. And it makes sense because if you look at this equation right here, this equation, vector x has to be a vector in Rn, and therefore to multiply by this, you have to represent x as an n by 1 matrix, or basically represent it vertically. So the m by n matrix multiplied by n by 1 matrix will give you m by 1 matrix, which is basically what a vector in Rn is going to be. So very important, make sure you understand the dimension of matrix A, because if you do it wrong, you find that your function is not properly defined and screw up the math. And next, what are these vectors? E1, E2 to En. Well, those are actually things that you learned back in chapter 2 of last year. So if you don't remember, these are things I taught you last year. You're going to have to remember some of these stuff. Otherwise, you're going to have difficulty with this class, because especially the linear algebra part, because you rely a lot on things that you learned back in chapter 1 and chapter 2 of last year. So what are the vector E1, E2 to En? The vectors vector e1, e2, dot, dot, dot to en, they are collectively called the standard basis. So what are the standard bases? These vectors take on a very specific shape. Vector e1 will be a vector to have a 1 at the first spot, which is identified by the subscript 1, and then 0 everywhere else. Vector e2 would have a 1 at the second spot, and then 0 everywhere else. And then this pattern continue to vector e sub n, which would have 0 everywhere except a 1 at the nth spot, which is the last spot. So they are called the standard basis collectively, and each one is just basically one vector within the standard basis. If you don't remember what standard bases do, you have to look up your notes from last year, chapter 1.1. That's when we talk about it. And I know it's a long time ago. I would say probably a little bit less than a year ago, because we would have talked about it like right in the beginning of school last year also. Now, once again, the theorem might seem confusing at first, but it's actually very simple. So show you an example to kind of illustrate what happened, okay? So suppose I give you this, and actually this concept actually very simple, because it just simply tell you to know how to form the matrix A that would describe the linear function correctly. So give you this example right here. And this is probably the most basic example I can show you. Suppose I have a function f that maps from R3 to R2. And let's say this function f is linear. Very important. So now before we move any further, look at this statement, and then also look at theorem 3.1. 3.1.3, and tell me, sorry, try to fix the 2 and then it's not working, and then tell me what dimension the matrix is going to be. So you think about it, this is R3 to R2, so 3 is n, 2 is m. So based on the theorem, you should have a 2 by 3 matrix, okay? So now let's consider the following. So once again, I told you this is a very easy example. The reason why, because I'm going to give you exactly what you need. So suppose given that f of 1, 0, 0 is equal to f of basically vector e1, which is equal to the vector 2, 1. F of 0, 1, 0 is equal to f of vector e2, and which is equal to 3, negative 1. And then f of 0, 0, 1 is equal to f of e3, and that's equal to negative 4, 2. Then what I'm going to ask you to do is go and find me the function f of vector x in matrix form. So how do we go about doing that? Well, so simple. The way to do that is to basically use theorem 3.1.3. And the way to do that is to simply use the information given to form the matrix. And how? Well, the theorem states that the matrix of the linear function is formed by using what happened to the function when you plug in the standard basis and whatever the output is together into a columns will form the matrix. So in this case, that's basically what we're going to do. In this case, the function f of vector x will simply just equal to the following. You have to equal to some kind of matrix multiplied by the vector x, y, z, which is what vector x is. And because of that, this matrix right here will have to be a 2 by 3 matrix. 2 by 3 matrix. And so therefore we have 3 columns. And each column would be kind of like a vector in R2. And guess what? We have 3 vectors in R2. So we just have to orient them correctly into a matrix. And how do I do that is based on the standard basis that we use. Standard basis E1 would go as to the first column. So therefore 2, 1 would be our first column. Standard basis vector E2 will form the second column. So notice that we're not putting these into column based on the order that are given to us, but rather on which vector they represent within the standard basis. So within the standard basis, E1 is the first vector, and therefore the output would go into the first column. E2 would be the second vector in the standard basis, therefore the output will go into the second column, and so on and so forth. So my last column would be this one. And voila. That's my function right there. Okay, so in this expression, in this function right here, this first column is what f of E1 is. This second column is what f of E2 is. And the third column is what f of E3 is. And if you have more, then you just basically continue to form the columns. And if each output has more dimension, then each column will be longer and therefore give you more row. Good? And it is very easy. The reason why this is very easy, of course, because I give you exactly what you need to form the matrix. I basically give you what f of E1, E2, and E3 is. And if you're thinking, on the actual test, that's not going to happen, is it? And your answer to that question, is, yeah, unfortunately, that's not going to happen on the test. So what happened is on the test will be more similar to what we're going to do next. Our next example will provide a little bit more math to figure it out. So let's take a look at what the next example will look like. Okay, our next example will be this one, which will be this. Let's say write the function f of vector x in matrix form. Oops. Given that f is linear, and we know that f of 2, 1 is equal to 1, 1, and f of 1, negative 1 is equal to negative 1, 1. So how are we going to proceed with this problem? So first of all, please don't write your matrix to be 1, 1, negative 1, 1. Don't just take the two output and put them as columns, because the input is incorrect. So what we have to do is to try to figure out what are we going to do with this. Okay, and the way to do that is the following. So to form this matrix, what we need is this. So here's what we need. We need what is f of 1, 0, and what is f of 0, 1, because those are the two vectors in the standard basis. So how are we going to do that? Well, the first thing you want to do is to figure out how to form 1, 0 and 0, 1 using the two input. So I'm going to show you how to start the process, and it's definitely something that you should be able to handle. So I'm going to go and show you the answer once I told you what you need to do. And again, you can simply just stop the video and just try to do what I asked you to do before you continue the video to see what the answer is. So what we need to do is kind of figure out what is 1, 0 in terms of 2, 1 and 1, 1. And what we basically want to do is to form a linear combination. So I'm going to go and say that let's say 1, 0 is some constant multiplied by 2, 1 plus some other constant multiplied by 1, negative 1. And now all I have to do is to go ahead and solve for A and B. So I guess we can just do this one together. It shouldn't be too bad to do. So if I do that, then this basically tells me that 1 is equal to 2A plus B. So 1 is equal to 2 times A, and then 1 plus 1 times B. 0 would equal to A minus B. So that tells me that A and B are the same, and then that would basically tell me that 1 would equal to 2A plus 1A, which is 3A. So A must equal to 1/3, so would be B, because A and B are the same. And so therefore, this tells me that 1, 0 is technically speaking 1/3 times 2, 1 plus 1/3 times 1, -1. And you can see that 1/3 times 2 is 2/3 plus 1/3 times 1 is 3/3, which is 1. And then 1/3 times 1 plus 1/3 times -1 would be 0. So now how does that help me? Well, remember, what I need to do is find f of 1, 0. So therefore, this would just basically equal to this. So now if I take f and we'll plug in 1, 0, I will now be able to figure it. Oh, wait. I won't be able to figure it out because I still don't know what function f is. Right? Oh, not true. Because we know function f is linear. Okay? Because function f is linear, that tells me that this right here, f of 1, 0, is technically the same as f of 1/3 times 2, 1 plus 1/3 times 1, -1, because I know 1, 0 is a linear combination of 2, 1 and 1, -1. And because the function f is linear, I can either combine this together into 1, 0 and then plug in the function f. Unfortunately, we cannot do because we don't know what function f is. Or we have a second option, like what we talked about yesterday. Option 2 is I can use the linear function property and say this is the same as 1/3 f of 2, 1 plus 1/3 f of 1, -1. And these two things we know because we're given. And so based on what we're given, f of 2, 1 is the same as 1, 1 and then f of 1, -1 is the same as -1, 1. So now I can actually combine them together to form my vector, which is 0, 2/3. Now, if you want to pause your video right now and try to find what f of 0, 1 is, you should do so now. And when you're done, you can then unpause and see the answer. So here's what happened, and I'm going to just continue. So the vector 0, 1 would actually equal to, this one's easy, it's just 1, 0 plus, plus negative, 1 times -1. Notice that we already know what f of 1, 0 is, so I can just use that to help me out. And then if I simply just do that plus negative of that, I just get 1 on the bottom and 0 on top. You could definitely do, I would imagine most of you probably try to do the same exact thing by using 0, 1 equal to something 2, 1 plus something 1, -1. If you do that, it's fine. You get the same answer, so don't worry. As a matter of fact, you should see that you have the same answer as I do. And so in this case, f of 0, 1 would just equal to f of 1, 0 plus -1, -1. And so that just equal to f of 1, 0 minus f of 1, -1. And f of 1, 0 is 0, 2/3. And then minus f of 1, -1 is -1, 1. So this is what we have. So 0 minus -1 is positive 1. And then negative 2/3 minus 1 is 1/3. So if you do it any other way, I would imagine, negative 1/3, I'm sorry. If you do it any other way, I would imagine you get the same exact answer like I do. And so now I'm ready to put in our function. So now that we know f of 1, 0 is equal to 0, 2/3, and f of 0, 1 is equal to 1, -1/3, then now I can define my function f of xy will be equal to 0, 2/3, 1, -1/3 times xy. And for your own sake, you should actually try to verify that it's true by plugging in 2, 1 and 1, -1 and see if that actually come out to be what the problem claimed that you should. There you go. So expect something similar to this on your tests. You will be asked something about theorem 3.1.3 where you go do something similar to this, and you will have to be able to figure out what f of the standard basis would be to form this matrix. Good. All right. There are plenty of homework problems that you can try out, so if you want to, you can definitely go ahead and do that. As a matter of fact, I'm going to go and give you 2 examples here, just to illustrate some more problems. So try to do these 2. So given a linear function f of vector x, where f map from R2 to R2, let's say A, let's say we're given this, f of vector E1 equal to 2E1, and f of vector E2 is equal to 3E2, find f. Oops. And then B, suppose I have function f of E1 equal to vector E2, and f of E2 is actually equal to negative vector E1, find f. So go and try those 2 out. If you want to definitely compare your answer, or you can post your answer on Google Classroom, or ask your friend for the answer and see if you get it correct. We can definitely talk about during class when if you want me to give you the answer, show you what to do. So next thing I want to talk to you about is this, a very important matrix that a very important linear function that have a lot of application. And as a matter of fact, you kind of learned it back in geometry, but you just didn't learn it in a matrix form. And that would be what we call rotation. So rotation is a geometrical transformation that allows you to transform something by rotating around some kind of central point. What we're going to talk about today is actually a way to define it algebraically. And you actually kind of learn some of these. You learn some coordinate rule that tell you what happens when you rotate something 90 degrees. But of course, here we're going to talk about something that rotate any arbitrary degree and how to define what happened to it. So if you think about it, the basic concept here is the following. Based on what you learn in geometry, if you take a coordinate, x and y, and if you rotate 90 degrees or 180 degrees or 270 degrees or 360 degrees around the origin, then that coordinate x and y will be changed into a different coordinate pair that cannot depend on what x and y would be. And if you so think about it from our idea, that would mean that we have to plug in 2 variables, x and y, and then this function somehow pop out 2 other variables that somehow relate to x and y. It's a classic example of a function that take in 2 variables and pop out 2 variables. A function that went from R2 to R2. And so this is what we call the rotational matrix function. If I define to be f of x equal to xy, then this matrix function will form this coefficient matrix A, cosine theta, sine theta, negative sine theta, cosine theta. This matrix has a name, is often referred to R theta. The R stands for rotation. So this matrix is called rotation theta matrix, which basically allows us to actually rotate a matrix any degrees by plugging in theta and then form this matrix. And then when you plug in an original vector, this matrix will rotate that matrix around the origin counterclockwise and give you a new output. Give you an example to illustrate. Some of you probably remember rotating 90 degrees. What would be the coordinate rule? And if I remember correctly, the coordinate rule is xy become negative yx. And show you why that is true. Suppose I do a rotation 90 matrix. Then that would mean that we have f of xy is equal to cosine 90 degrees, negative sine 90 degrees, sine 90 degrees, cosine 90 degrees. Yes, in the rotation matrix, we usually use degree measurement just because it's more common. But you want to, you can definitely say rotate pi over 2 matrix, and then we do everything in radian. It will be the same. Multiply by xy. So what happened to this matrix? Well, then you need to know what cosine 90 and sine 90 is. So if you remember, cosine 90 will be 0. Sine 90 is 1, so it'll become negative 1 here, and 0. And when I multiply this out, that just basically become negative yx. Voila! That's the same formula you learned back in geometry. Interesting. We'll definitely verify another one. So how about we do this one? We do r of 180 degrees. So that will be f of xy is equal to cosine 180 degrees, negative sine 180 degrees, sine 180 degrees, cosine 180 degrees, times xy. And that will come out to be negative 1, 0, 0, negative 1 times xy. And that just becomes negative x, negative y. Voila. There you go. Interesting. You will need to know the rotational matrix for your upcoming tests. So please make sure that you memorize it. All right. So the next thing I want to talk to you about is the following. Some of the important properties about linear function and how that affects what we need to do with differential equation. So one of the important things that we need to learn about linear algebra in relation to differential equation is the concept of linear combination from last year. Okay, so and also some of the geometry that we learned last year about how linear combination work. So let's see if you remember this. So this is theorem 3.1.4, which states the following. If the function f that met from Rn to Rm is linear and has a matrix A, then what we know is that the image of f will be all possible linear combination of the columns of A. So what does that mean? That basically meaning that I could actually rewrite the linear function f not as a matrix form, but as a linear combination form. And how does that change the way we represent it? Well, it doesn't really change what we try to represent, but it does change the way we look at the output in a geometrical way. So show you how that is, what that means. So give you an example. Okay, suppose I have a function f that maps from R2 to R3. Okay, and let's say f is linear. And as a matter of fact, from this point on, mostly almost all functions that we're going to talk about will be linear. Okay, let's say f is linear. And let's say we're given that f of vector e1 is 1, 2, 1. And f of vector e2 is going to be negative 1, 0, 3. So now that we have everything, we're going to try to rewrite this function. So let's say this function f of xy would equal to, so notice using theorem 3.1.3, I'll be able to use these two vectors to form the columns of my matrix. So 1, 2, 1, negative 1, 0, 3, multiplied by the input, oops, wrong variable. variable x and y. Now, here how we're going to rewrite this. So let's go and try to see what happened here. So if I multiply this matrix, which is 3 by 2, times the vector here, which is 2 by 1, what I get will be a 3 by 1 matrix. So based on matrix multiplication, it will be 1, negative 1, dot product x, y. So become x minus y. 2, 0, dot product x, y become 2x. And then 1, 3, dot product x, y become x plus 3y. Now, notice that when I wrote this, I line up the x and the y. And you should do that too. So now what do I do with this? So how about we do the following? We go separate. We go separate this into two vectors. Okay? Now, something very interesting here. Notice that I didn't put minus, but I put plus, and I put the negative here inside the y. Remember, we talked about this last year. When you're forming like some vector like this, you probably almost always want to have the plus sign instead. And all the negatives just go inside the vector. It makes it nicer when you form your vector this way. So if I do that now, it becomes just a sum of two vectors. This vector is x, 2x, x, and this one negative y, 0, y. Now notice the first vector, all of them have an x in it. So what I'm going to do is I'm going to pull out the x. And then for the second one, I'm going to pull out the y. If you are looking at this like, wait a minute, doesn't these two vectors just basically the two column? Yes, that's the point of 3.1.4. 3.1.4 tell you that the output of the function are just linear combination of the columns of the matrix. And that's what we have right here. We basically have these two columns, and then with some coefficient in front, which form a linear combination. And since x and y can be any value, therefore form all possible linear combination. So this is a linear combination because x and y are the two scalar in front of the two vectors. So linear combination between two vectors, which is 1, 2, 1 and negative 1, 0, 3. And since x and y can represent anything, that therefore become all possible linear combination. Now here's something that I hope some of you remember. So if you're looking at if you're watching the video and you remember this, great, good job. That means you pay attention last year. And if you don't remember, it's okay. It's long ago and you might not remember. We talk about something in chapter 2 when we talk about solving system of linear equation. And when we talk about the solution set being infinite, we realize that even though the solution set could contain infinite solutions in it, but it can take on a different geometrical shape based on how the solution set is represented. And here, notice that we have something that might remind you of what you learned back in chapter 1 of last year, as well as more in detail in chapter 2. But if you think about it, what we basically have are two vectors with two scalar, or two variable represent scalar in front of it. And the proper way to actually state this is that x and y actually can be represented as perimeters, and then these two vectors actually could be considered to be direction vectors. And if that's the case, then this expression right here actually represents what we call a two-plane. You can think of them as actually a plane exists in R3. But mathematically, we want to call them a two-plane. So what do I mean by two-plane? Well, this is basically what it means. This right here, this expression right here is basically called two-plane because it has two direction vector, and in R3 because the direction is actually in three-dimensional. So what is a two-plane? So here's one way to define it. A k-plane in Rn is basically the image of a linear function f that went from R sub k to R sub n. So if you have a function that went from Rn to Rm, the domain dimension right here, that indicate what dimension plane you're creating, and then this will be the output where the function residing. Now in this notation right here, obviously we are talking about x, k being less than n. If it's greater, it won't be able to form it, and if it is indeed greater, then what would happen is that the plane would actually collapse. And we'll talk about that a little bit more in detail later on. Okay? So I know the video is kind of long, but I do want to just talk about one more thing before we're done for today. We use a lot of this terminology like the term image and things like that, and I do want to kind of define them properly. So this would be the last thing I want to write about for you. It's the following three terms: domain, range, and image. So they actually define slightly different than, once again, your math teacher in the past lied to you a little bit. So we're going to try to define these three things. So suppose given a function, let's say f map from D, oops, sorry, D to R. In this expression right here, D is referred to as the domain of the function. Basically meaning the set of all possible input. Anything that you want to plug into the function, that basically considered a domain. Okay. R is called the range of the function. The set of all possible output. And so what is image? So let's say let E be a subset of D. Then f of E is basically called the image of E within the range. So therefore, the image is not the output of the function. Image is the output of the function. Range is just all possible output. And if I say f of the entire domain, that's basically called the image of the function. Now, I know it might sound a little confusing, but actually it's not. I'll show you. In a previous example, we have f that map from R2 to R3, which is this example right here. So in this scenario right here, the input, which is the domain would be any vectors that's in R2. And then the range is actually any vector that's in R3. Now the problem is this function doesn't actually give out every single vector possible in R3, but instead it only gives out a two-planed within R3. Now, you can definitely think of an example that would do that, but unfortunately, this video is getting long. So I'm going to actually probably talk a little bit more about it during class. So help you understand the concept between domain, range, and image. And then we're going to continue this on our next video. My next video could be the last video for 3.1, depending on how long I'm going to take, or might be, at most, will be 2 more videos, then that will be it. So that's it for today. We're going to continue some more tomorrow. Okay, bye-bye.